All right, so good morning. We're gonna pick up from where we left the last time. Uh, the last session, so this is session number 4, and then the last session we did, we look into velocity. We look at the velocity time graph, and we said that the slope of the velocity time graph is acceleration, and in order for acceleration to occur, you need to have a change in velocity. So that's important. When we look at the velocity time graph, the position of the velocity time graph, whether it's if the velocity is negative or positive, it tells you the direction of travel. So when we denote a velocity as positive, that means it's moving to the right, or it's going up, a motion uh, of something going up. And then a velocity that is negative denotes motion that's going to the left, or something is coming downwards. Um, we look at the slope of the velocity time graph. If the slope is sloping upwards, then we call that a positive acceleration. If it's sloping downward, then it's negative acceleration. So those things are very important. And then we top it off with free fall. So we're going to continue with free fall this morning. So when we say something is in free fall, the only force acting on the object is the force of gravity, um, pulling the object downwards, and we tend to neglect air resistance. Um, but for simplicity, if something is dropped, if something is dropped from some height, then it's going to be under the influence of gravity, and that is an example of free fall. So if you drop a ball, just imagine you drop a ball from some height. Before you drop the ball, the time is 0 seconds, the velocity is 0 meters per second. After you drop the ball, because the acceleration of gravity, the acceleration of gravity is a constant number and it's not going to change. The acceleration of gravity is 9.8 meters per second square, or 9.8 meters per second per second. What that is saying is that every second the velocity is going to change by 9.8 meters per second. And we usually put a minus before the acceleration due to gravity to denote the direction of travel, because gravity is a pull downwards. If you have a rocket going up, then you would denote that acceleration as a positive number, but acceleration due to gravity is a negative number. So for the first, so at time 0, the velocity is 0. At time 1 second, the velocity is going to increase by 9.8 meters per second. For the second, the velocity increased by another 9.8 meters per second. So the total velocity would be 19.6 meters per second. And for the third second, it increased by 9.8 meters per second again, to give you a total velocity of 29.4 meters per second. And for the fourth second, it increased another 9.8 meters per second. So what we're saying is that every second the velocity will increase by 9.8 meters per second. And that is what the acceleration of gravity is telling you. Okay? Every second the velocity increased by 9.8 meters per second. Remember, acceleration is a change in velocity. You cannot have acceleration unless you have a change in velocity. That's the definition. Okay. This is just to give you, a slightly more accurate perspective of free fall. What I showed you is a very simplistic uh, approach to free fall. But if you look in free fall in a little bit more detail, say you have a rocket which is falling to Earth, a rocket which is falling to Earth. The weight of the rocket is going to pull it downwards, okay, because of the acceleration due to gravity. Weight, remember, the weight is mass times acceleration, and the acceleration here is the acceleration due to gravity, which is g. So that's pulling it downward. And then the air resistance and all of that, which is pulling it upwards, we call that the drag force. Drag force. But the net force pulling the rocket downwards is the difference between these two forces. The weight pulling it downwards and the drag force pulling it upwards. So, when we talk about drag, the things that influence drag is the the density of the air, the velocity of the object, the area of the object, and what we call the drag coefficient. You don't have to remember this, but just remember that drag is pulling the rocket upwards. Okay, and if a very simplistic approach is the resistance that the air poses to the rocket. So the net force pulling the rocket downwards is the drag force minus the weight. And again, the drag force is influenced by the drag coefficient, the frontal area of the rocket, the gas density. So we're talking about the air, the density of air, and the velocity of the terminal velocity of the rocket. Okay, so this would be an actual scenario, but when for our purposes right now, we assume that the air resistance is negligible. If you remember your position time graph, so your position time graph, the slope of the position time graph is your velocity. So when you have a free falling object, uh, the velocity when you drop something, if you drop an object and it's on the free fall, at time zero, the velocity is zero. So that's what this point here represents. Okay, the position you're going to be at certain height, and that is why you have the vertical portion of this position time graph has a number. At time zero, it is at a certain height because you're dropping the object. But if you look at the slope, it's horizontal. So the slope is zero. So at time zero, you have no velocity because you're holding the object. And then when you drop the object, it starts slow. Look at the slope. It starts slow. And then as the slope increases, it tells you that the velocity increasing. So, the velocity gets very high because the slope is a large number. So the velocity gets very high until time zero, the position is going to be zero. So when it comes all the way down, sorry, not at time zero, at some time later than time zero, the position becomes zero because it's now on the ground. So This is a position time graph depicting free fall. Okay, at time zero, you start at some height. Okay, so on the position time graph, the vertical axis is the position, so it starts at certain height, and then the velocity is zero because you're holding the object, and you're going to drop it. Okay, you can see that the slope of your position time graph is there's no slope, it's horizontal, so that tells you that the velocity is zero. Then when you drop it, it starts slow. Look at the slope. Remember, the slope of the position time graph is your velocity. So it starts slow, and then as the slope increases, it tells you that the velocity is getting greater and greater and greater and greater until some time later, when it hits the ground, the position will be zero, time will be some number. Okay. Okay, so that is the position time graph for free fall, uh, as opposed to your velocity time graph. So this is your velocity time graph for free fall. Velocity time graph for free fall. All right, so your velocity is on the vertical axis and your time is on the horizontal axis. Positive velocity is above the horizontal, negative velocity is below the horizontal. Okay, and remember, it's going to be negative velocity because the object is coming downwards. Okay, if the object was going upwards, it would be in this portion of your time graph. But because the object is going downward, if the object was going to the left, it would also be in this quadrant. So it's in this negative quadrant. So remember, this horizontal line represents time. So positive velocity is up here, negative velocity is down here. So because the object is coming downwards, it's in the negative quadrant. But as time increases, the velocity increase because it's on the free fall, it's on the gravity. So even though it's negative, you can see the number is increasing. So again, at time zero, velocity is zero because you're going to drop the object from some height, but this is not a position time graph. This is a velocity time graph. So at time zero, it has a zero velocity. At say time 1 second, okay, at time 1 second, the velocity is 9.8 meters per second. At time 2 seconds, going to be 19.6. Remember that? And then at time 3 seconds, it's going to be three times that. Okay? So when you plot those points, you get the straight line. Remember, the straight line, the slope of the velocity time graph is the acceleration. So if you were to calculate the slope of this, you're going to get 9.8 meters per second. Negative minus 9.8 meters per second, second per second, all right? Because it's sloping in this direction. So the slope of this uh, velocity time graph is 9.8 meters per second, or 9.8 meters per second square. Okay, it's in this quadrant because of the direction of travel. It's coming downwards, so that's why it's in this quadrant. And you can see every second the velocity increase by 9.8 meters per second. All right, so if you were to look at the different uh, look at the different motion for free fall with the velocity time graph as we just showed, it's going to be in this quadrant of your velocity time graph. The slope of the velocity time graph tells you about the acceleration. Okay, the velocity is going to be negative because it's a movement or a motion downwards. For acceleration, okay, for for the acceleration, if this is an acceleration time graph, that is you're plotting acceleration against time, okay, it's going to be a negative number. So this is your positive quadrant. This is the negative quadrant below the the horizontal uh, timeline, okay? Because it's a motion downwards. So it's going to be in the negative quadrant, and it's 9.8 meters per second square. And again, for the position time graph, at some position, at some height, the time at time zero, it's going to have some height, whatever that is, and then as time goes, it starts slow because at time zero, it has certain height, but the velocity is zero, and the slope is horizontal. But as time goes on, you can see the slope gradually increase. Tell you that you know it's speeding up, and then at some time later, the position is zero. That means it's on the ground. So this is you may be asked to do a graphical representation of free fall. They may ask you to do a velocity time graph of free fall, or acceleration time graph of free fall, or a position time graph of free fall. So if you understand it, you can always do the graphical representation. All right. So when we talk about free fall, and let's go back to this. So let's use the velocity time graph. So what we had said before is that the area under the curve of a velocity time graph represents the displacement or distance. For simplicity, say distance. What we're saying is that this area under this triangle, this area right here, this area, the area under the curve is distance. So this area is distance or displacement. And we're going to use them interchangeable for the time being. But the area under this triangle is the distance traveled. Now, the area for a triangle is half the base times the height. Okay? The area for a triangle is half the base times the height. Okay? So so whatever time, so the time is on the horizontal axis, velocity is on the vertical axis. So if we take half the times the velocity, we get the displacement or distance. Okay, so let's look at what that looks like. So okay, so this is very important now. Um, so let's look at it. All right, so the displacement is equal to the area under the curve. And just showed you that displacement is equal to it's a triangle. The area is a triangle, so half the base times the height is equal to the area. Remember that the acceleration is equal to change in velocity with respect to time. We're talking about free fall. So when we talk about change in velocity, we talk about the final velocity minus the initial velocity over time. But because the initial velocity, we drop in the object. The initial velocity is zero, so we can just represent acceleration, and this is acceleration due to gravity, so we can put it as g is equal to v, which is vf, final velocity over time. Okay, so if you were to rearrange this equation, then the final velocity is equal to acceleration times time and this is acceleration due to gravity. So displacement is equal to, when you plug it in this equation, the displacement is equal to let's go back here. So this is the original equation from the area under the curve, but we know that acceleration is equal to final velocity minus initial velocity over time. So initial velocity is 0. So the final velocity is equal to acceleration times time when you rearrange this equation. If you plug this V inside here, because V is equal to acceleration times time, you get this. So the displacement is equal to half acceleration times time. Just plug it in this equation. So the displacement is equal to half g, which is acceleration due to gravity, times time. So this is the equation we use for free fall, and I just showed you how this equation is derived. So when you know how to derive an equation, then it sticks. You understand what you're doing. So for the displacement, when you drop an object, this is the displacement for free fall. So when you drop an object from some height, you can find the distance traveled by just knowing the time it takes. So if two persons are doing this experiment, you can time when someone drops an object, you can time it, and just from the time, you can calculate how far up the person was when they dropped the object, because displacement or distance traveled is equal to half or 0.5 times g, acceleration due to gravity, times time squared. So once you calculate the time, so that's an experiment you can do by yourself, or you can do with someone else. Okay, person drop an object, you time it to see what time it takes to hit the ground, and you can calculate the distance the object traveled. Then you can measure it to see if your experiment is correct. All right. So again, the area under the curve, okay? So the area under the curve is equal to half the base times the height, okay? Because a triangle is half of a rectangle. The area of a rectangle is the base times the height. And triangle is just a right angle triangle is half of that. So you get half base times the height. So remember that the area under the curve, half the base times the height. Once you remember that, then you can derive your equation. So when you see this, when you see your equation for free fall, distance is equal to half or 0.5 times g times time squared. You know how that came about, how to derive it. Again, for an object that is dropped from rest, okay, at time 0, velocity is 0, and then the velocity gradually increase. Every second, the velocity is going to increase 9.8 meters per second, okay? And that is why it's in the negative portion of your velocity, because the object is moving downwards. It slopes downwards, hence the slope, which represents your acceleration due to gravity, is going to be 9.8 meters per second, or 9.8 meters per second square for free fall. So these are some kinematic equations, and we will derive them, okay? They look very complicated, but if you know how to derive them, then it's not so bad, okay? You will remember it a little bit more, okay? This okay, so we'll derive them, but these are the kinematic equations, and what, as we had mentioned early on, you know, for the first one, you have distance, you have initial velocity, you have time, you have acceleration, and you have time. So if you want to find the distance traveled by an object, and you have the initial velocity, you have the time and acceleration, then you can calculate the distance traveled. Okay, but we'll come back to these later on. All right, and we will show you how to derive these equations. But this one is relatively simple because this one is just the definition for acceleration. So this one is very, very simple. Remember, acceleration is equal to change in velocity with respect to time. So the acceleration is equal to the final velocity minus the initial velocity over time. And if you solve for final velocity, then you get this equation. All right, so let me just show you. So this one is relatively simple, and then we'll at uh, some later date we'll derive the others. So if you remember, acceleration is a change in velocity. Change in velocity is the final velocity, so we call that VF, minus the initial velocity with respect to time, or divided by time. Okay, so just using the definition for acceleration, which is the change in velocity, final velocity minus initial velocity over time. Okay, so then your change in velocity, which is VF minus VI, initial velocity, is equal to acceleration times time. Okay, so final velocity minus initial velocity is acceleration times time, just using that. So final velocity, then, if you carry initial velocity over to the other side, that is equal to acceleration times time. Sorry, this is, oh my god. So this is a times, okay? It's not a new symbol in math. Okay, this thing is possessed, so, all right, so this is, all right, so this is acceleration times time plus VI, which is initial velocity. Okay, so that is how you get this equation. As time goes on, we'll derive the other equations. So when you see them, you're not intimidated by them. Okay, so you can find out the final velocity if you know the acceleration. Acceleration is acceleration due to gravity for free fall. If you know the time, okay, we know the initial velocity for free fall would be 0. So the final velocity is equal to the acceleration due to gravity times the time. You know the acceleration due to gravity. So if you know the time that the object takes to strike the ground, then you can find the final velocity. So that's the kinematic equation, and as I said, we'll explain them. I will derive them at a later date, so you're not intimidated by them. All right. So again, when we talk about free fall for an object dropped from rest, the displacement, and I showed you how to derive that, the displacement or distance traveled is equal to 0.5 times g times time times time, or it's 0.5 g times time squared. Okay, so if you know the time it takes to hit the ground, you can calculate the height of the object. All right. So object propel upwards. So, just when we come to projection or projectiles, we will go into this in a little bit more depth. But if you have an object that is projected upwards, okay, just imagine you build a little rocket and you propel your rocket upwards. At the height of the at the peak of the trajectory, your final velocity is going to be zero. So what we're saying is that when you project your projectile upwards, before it comes down, that velocity before it comes down is going to be zero. And again, remember, we're going to go into this again. But when you project something upwards, at the point where it starts to come down, that final velocity is equal to zero, because when it goes up and it's coming down, it actually after the velocity, it has to stop. You think, if you think about it seriously, when you project something upwards, it stops before it starts coming down. Just think about it. It stops because it can't come down unless it stops. So at the height of that trajectory, the final velocity is zero. So object projected upward, velocity at projection is equal and opposite in sign when it returns to the same height. So what this is actually saying, and we're going to go over this again, is that when you project it upwards, you're going to start with an initial velocity. It's going to travel upwards, then it's going to stop and then start coming down. At every point when it's coming down, the velocity is going to be the same, but the sign is going to be different because it's moving in the opposite direction. And let me give you a quick representation of what we're talking about. So, you project an object upwards like this. Okay, so when you project the object upwards, okay, at this point, it's going to be, the velocity is going to be zero because it's now coming downwards. Okay, so this is what we'll call the final velocity. So at this point, take this point for example, you're going to call this velocity x. At this point, call it velocity y. So velocity y. And then at this point, call it velocity z. Okay, it's moving upward, so the velocity is going to be positive. Remember, it's moving upward, velocity positive. At this point here, at this final velocity, the velocity is zero because it started coming down. So this is Vf, and Vf is equal to zero because it's gonna stop before it comes down. Okay, what we're saying is that when it starts coming down, at this point right here, the velocity is also going to be velocity z, whatever the number z is. Okay, the velocity is going to be z at this point, the same point corresponding to when it's going up. The velocity here is going to be zero, but the sign is going to be negative because it's coming down. At this point right here, the velocity is going to be y, whatever number y is. So this is going to be velocity y, but it's going to be negative velocity because the object is coming downwards. At this point right here, it's going to be velocity x, but it's going to be a negative velocity because the object is coming downwards. Okay? So if you know these velocity at different points, if you know these velocity, you also know this. It's just that the sign changes because of the change in direction. Okay, so when we come to projectiles, we'll go over that in a little bit more detail, but that's what that is saying right there. All right. Newton was a British physicist who give us most of our information about motion of objects. Okay, if you want to look at Newton as the father of physics, because he's the one who, you know, opened our mind to motion in tremendous detail. Before Newton, of course, you had, you have Galileo, but for I would say for modern physics, Newton is one of the founding fathers. And Newton has three laws. Okay, we're going to look at the first law. So Newton's first law of motion. So his laws describe motion, and we use these laws in physics to describe motion in details. So Newton's first law, also known as a law of inertia, okay, states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and direction unless acted upon by an unbalanced force. So this is something you have to commit to memory, but you have to understand what it's saying. What Newton is saying is that if you have an object, say your book is on the table, your book is going to stay on the table, not moving, okay? Or if you throw your book on the table, so you throw your book on the table, or you push the book on the table, your book would stay in motion with the same speed and same direction unless it's acted upon by an unbalanced force. And the term unbalanced force is very important. Okay, so when your book is on the table, say, your book is stationary on the table, the book is pressing downwards on the table, with a certain force, and we'll go over what that force is. And then the table is also pushing on the book with an equal and opposite force. Okay? So first, the book is on the table, not moving. The book is going to exert a force on the table downwards, and the table is going to push up on the book upwards. That is a balanced force. So there's no unbalanced force there because the book is pushing down on the table is pushing on the book, same force. So those are balanced force. In order to move that object, you need an unbalanced force. So if you push the book, then that's an unbalanced force. Okay? So what he's saying that an object at rest stays at rest unless acted upon an unbalanced force. So again, the book is pushing down on the table with a certain force, and the table is pushing up on the book with a certain force. Those two forces are balanced, so you're not going to get any motion at all. And in the other scenario, what he's saying that if you push a book and the book is sliding on the table, okay, if the book is sliding on the table and there is no friction, so he didn't, the book, so if you eliminate friction, that book will move in the same direction and speed unless it's acted on by an unbalanced force. Okay? So you have to remember Newton's first law, and you have to understand what he's saying. So, in essence, what he is saying is that objects tend to keep on doing what they're doing. Okay? So, the book on the table will stay there. If you push the book on the table, it will keep on moving. Okay? If you eliminate for friction, that is. Okay? So, if you were to look at Newton's first law in everyday activity, say, look at the football. So, soccer. So, and this is a soccer ball, uh, or in in other circles, this is a football. So this is if the ball is on the turf, so an object at rest. So this is at rest. It's gonna stay there. If there are no outside influence, the ball is the ball has a certain amount of weight, and the weight is gonna pull it downwards. So we'll so the force of the ball on the turf is downwards, and we'll go over what weight is. Weight is a force which is downwards, okay? And then the turf is pushing up on the ball with a certain force. These two forces are balanced. So these are balanced force. This is an unbalanced force because everything was in perfect order, but this unbalanced force, if it strike the ball in this direction, okay, then the ball is going to move, it's going to be in motion, and it will continue same speed, same direction, unless it is acted on by an unbalanced force. If you eliminate resistance, air resistance, and stuff like that, it will just continue to move uninhibited. If it's acted on by an unbalanced force, so if you have a net, so if the ball was kicked into the net, then the net becomes the unbalanced force. It prevents the ball from moving further. So that's a practical description of Newton's first law. So, so when we say an object is at rest, then we're saying that the velocity is equal to 0 meters per second. Acceleration is 0 meters per second square. So this is an object at rest. And if the object is in motion, then it is going to have a certain amount of velocity. It's going to be greater than 0 meters per second. Acceleration is going to equal to 0 because we're talking about a motion with constant velocity. Because if the object is in motion and it's not acted on by any unbalanced force, we're talking about a constant velocity. If the velocity is constant, then you're not going to have any acceleration. So Newton's first law talks about object with constant velocity, no acceleration. Then it's going to stay in motion, the same speed. Same speed means that the velocity is not changing and in the same direction. So Newton's first law talks about a motion without acceleration. Okay. Um, so and then you can use a rocket to also depict Newton's first law. So every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change the state of forces, unless it's compelled to change that state by forces impressed on it. Saying the same thing, okay? But once you understand the law, you can describe it in whatever terms you want to describe it in. So object in a state of rest, the airspeed is 0 because it's at rest. The engine fire thrust increase from 0. The weight decreases, and so basically saying the same thing. Object at rest will remain at rest. Object in motion will remain in motion with the same speed and direction unless acted upon by an unbalanced force. So the unbalanced force is a very important number. So inertia, let's look at inertia and mass, because these are important terms. And Newton described these, so you have to have an understanding of what inertia and mass is. When we talk about inertia, it is a tendency to resist changes in a state of motion. So the more inertia an object have, the more it's going to resist a change in its state of motion. So if you have a small ball, you can change the state of a motion of that ball quite easily, as opposed to you have a huge boulder. If you have a huge boulder, to change the state of motion of the boulder, it's going to be, it's a lot of resistance. So the small ball is going to have less inertia than the huge boulder. Okay? So inertia is the tendency to resist changes in its state of motion. So the resistance, or another way to describe it, the resistance an object has to a change in its state of motion. The more inertia it has, the more it's going to change, it's going to resist change in its motion. The less inertia an object has, it's easier to change a state of motion. Okay? So, inertia is the bigness or the weightiness of an object. Okay, so the more inertia, the more it's going to resist a change in the state of motion, or the greater the resistance the object is going to have to a change in its state of motion. So inertia, get a good concept of inertia. Okay, so again, if you have an object 300 kg, object 30 kg, the 300 kg is going to resist a change in its motion more than this one. So the larger object have more inertia. It doesn't necessarily mean the largeness of an object have more inertia. It is the because if the smaller object is much more dense, then it can have more inertia. So an object will not change its motion unless acted on by an unbalanced force, Newton's first law. If it is at rest, it will stay at rest. If it is in motion, it will remain at motion in the same velocity and direction. An object with a greater mass have more inertia. So mass and inertia is sort of synonymous. So an object with a greater mass will have more inertia, and it takes more force to change its motion. Okay? So before Newton, then you had Galileo, which described moving objects, and what he said, moving objects stop because of a force called friction, which technically is correct. It's more than that, but he was correct. And then Newton came along and stated that a force is not needed to keep an object in motion. Object will continue to move with the same speed and same direction unless it's acted on by an unbalanced force. So what Newton was saying is that if the velocity is constant, so if an object is moving with a constant velocity, remember constant velocity, the acceleration is zero, no change. So for you to get acceleration, you need a change in velocity. So with Newton moving object, the velocity is constant, acceleration is zero. Force is equal to mass times acceleration. So, and we'll come to that, Newton's second law. So if you have no acceleration, you have no force, because force is equal to mass times acceleration. So what Newton is saying, If an object is in motion, you have no forces needed to keep that object in motion because force is equal to mass times acceleration. Okay? You know, so these are just other explanation of Newton's first law. And then, so we talk about inertia. So a mass is a measure of inertia. Okay? It's that quantity that is solely dependent upon the inertia of an object. So again, the inertia is the object resist changes in their motion or velocity. Okay, so mass is just a measure of inertia. So we're gonna stop here, and we're gonna stop here, and then so go over